Before we get started with our presentation, let me just take a moment to review this On24 platform with you. All your windows are movable and resizable on your screen. Some can be expanded to full screen. Your main viewing area is the live screen view, and you may also use the media player window. If that is utilized, that will expand automatically on your screen. If you accidentally close a window instead of reducing it, just click on the icon corresponding to it and it will reopen for you. If you're on a Wi-Fi connection, we do recommend closing any applications or browsers that you are using to conserve bandwidth and reduce potential connectivity issues. If you are not hearing the audio or if the slides do not advance, press F5 to refresh your screen. And this session will be recorded and available to you in a few hours following the session so that you can go back and review anything that you may have missed. We do encourage you to interact with us. Please submit your questions in the Ask Question window. And if you are viewing this on demand, you can also submit questions and they will be forwarded to our presenters. Check the related content, which is in the upper right corner on your screen, for any additional resources and links that you may find helpful. And if you would like to enable closed captioning, please press the CC icon in your media player. Now for today's presentation, we're joined by Sean Johnson and Fasil Khan of our Geotechnical Engineering Group working with PLAXIS. And let me turn it over to Sean for introductions to get us started.
Hello, everybody. My name is Sean Johnson. I am an application engineer over at Bentley Systems working in the PLAXIS group. I have a master's degree from MIT focused on finite element modeling, and I'm a registered professional engineer in the state of Utah, geotechnical engineer. Fasil Khan, would you like to give your introduction?
Hi, yes. So this is Fasil. I have a background in civil engineering and a specialization in geotechnical engineering with a PhD from University of Regina in Saskatchewan, Canada. And thereafter, also before that, for my graduate studies, I have like some 7 years of consulting and construction experience in Pakistan. And since then I moved here and then to US, where I joined Bentley Systems, and now I provide numerical technical support for PLAXIS and PLAXIS LE softwares. So that's my background. Sean?
Thank you, Fasil.
Yep.
As mentioned earlier, this is a answer hour focused on generating the correct initial stresses in your PLAXIS model. Our intention is for the presentation to be quite short and to have the majority of the time reserved for your questions. So if you have questions relevant to this topic, please let us know. With that being said, I will begin the presentation. So the initial stress state in PLAXIS is determined in your initial phase or phases. How the initial stresses are determined is based on a number of factors. Those include the soil weight of the soils you're using in your model, the loading or stress history of those soils. So this specifically relates to soils pre-consolidation pressure, or it can also be defined as an over-consolidation ratio. And the pore pressure and flow velocities also will determine the initial stress state. In PLAXIS, we have 4 calculation types that will generate initial stresses. Those include the K-0 procedure, gravity loading, field stress, and if we're only concerned with the groundwater flow analysis, we can select flow only, and those will neglect any stresses, effective stresses that are developed due to the soil weight. I will begin to discuss how the K-0 procedure works. So a K-0 procedure is a direct calculation of the stresses from the coefficient of lateral earth pressure, also referred to as K0. So the way this works is in the material definitions, we'll need to define a OCR, or pre-consolidation pressure. POP is just an acronym for pre-consolidation pressure. So what will happen is the program will automatically calculate the vertical total stress based on the unit weight of the soil, which we've defined in the material properties. It'll find the effective stress by subtracting the pore water pressure. From the effective stress, we can find the horizontal stress by multiplying by the K0 value. In PLAXIS, PLAXIS by default uses what's called the J-key equation, which would relate the coefficient of lateral earth pressure in the normally consolidated state equal to 1 minus sine of the friction angle. If the soil is overly consolidated, then the OCR has an effect on the K0 value, and the K0 value will increase as a function of OCR. Then based on that K0 value multiplied by the vertical effective stress, we can get the horizontal effective stress. And you can see here is a handy diagram that illustrates the principle of the initial stress generation using K0 on this sloped surface. What's interesting here is that we see that the principal direction is equal to the vertical and horizontal plane. So there is no shear stresses generated, even though we have a slope. And this is one disadvantage of using the K0 procedure. Specifically, that shear stresses are not generated because of the way the stress generation procedure is performed. And because shear stresses are not generated, equilibrium is not guaranteed. However, this K0 procedure has advantages, specifically because we reduce everything into the horizontal and vertical principal directions. We can take into account OCR, and we can, from taking into account OCR, we can fine tune what the K0 value should be. So I should also emphasize again that the K0 value, or K0 value, the OCR, and the pre-consolidation pressure are input parameters you define when you define the soil. So there's a tab where you can see where these values need to be defined. If you don't define them explicitly, PLAXIS will automatically calculate them, assuming that OCR equals 1 and K0 is equal to 1 minus sine of your friction angle. So the next option to generate initial stresses is called gravity loading. Gravity loading is a different calculation procedure than K0 loading. How gravity loading works is it makes a direct calculation depending on the unit weight of the soil and the Poisson's ratio of the soil, and develops an initial stress state based on those two factors. So PLAXIS will use the unit weight of the soil and the orientation of the elements generated and generate a stress field based on that. However, because it's based on the Poisson's ratio and not the OCR or the K0 determined from OCR, the K0 in this case is a function of the Poisson's ratio, specifically Poisson's divided by 1 minus Poisson's. So we'll get a stress field. However, that stress field will be independent of OCR. And because it's independent of OCR, this gravity loading can only really work if we have normally consolidated soil. However, an advantage here is that we can generate initial shear stresses. You can see here in this diagram that we got a visual description of the principal stress directions on the slope. And you can see here that it follows the geometry of the slope. So here we're mobilizing initial shear stresses. Those will and a shear stress will mobilize a shear strain. And then we're able to, from this, we get an initial stress displacement, which is set to 0 in the following phase. This is an internal process in the calculation. What's important to note here is that when you use gravity loading, it only really is applicable if you have a normally consolidated soil but it can capture the initial shear stress state. Discussing gravity loading further, we need to select the ignore undrained behavior to avoid generation of unrealistic excess pore pressures when we define the gravity loading. And then the program will automatically reset displacements to 0 in phase 1 to discard all the displacements caused by the initial shear stress generation. So as I mentioned earlier, because the program is making a direct calculation that mobilizes shear stress, will generate shear strains. And then we need to reset those to 0 when we begin our analysis. So we need to select the option to reset displacements to 0 in the following phase. By default, this is automatically done, so you don't need to do it deliberately. Gravity loading can take into account steady-state groundwater flow or steady-state thermal flow, and it can include the effect of suction. How suction works is that when you have a soil that has a water content greater than 0 but less than 1, you'll develop capillary stresses in the soil due to the suction effect. And the suction effect would be shown as an effective stress inside the soil. We can activate or deactivate that in the calculation control parameters window. One final note is that if you're using gravity loading and you have an advanced model that takes into account creep behavior, because creep behavior is a time-dependent behavior, we need to define a time interval because by default, if you're using a soil such as soft soil creep, everything is normalized to 1 day. So if we would want to have an initial stress state that has that captures the creep state after 1,000 days, we would need to, in the initial gravity loading phase, set a t equal to 1,000 days. The third option we have to define the initial stress state is called field stress. So in the previous two options, K0 and gravity loading, the program does an internal calculation to determine the initial stress state. However, with field stress, the difference is that you are fully controlling the initial stress generation in the model. So we just simply tell the program in the initial stress state, we want each principal direction to have a certain magnitude of stress. And this will be applied all over in your model. So we fix the values, the magnitudes of the principal stress directions, sigma 1, sigma 2, and sigma 3, and they'll be applied over the entire model. No gravity is taken into account, so it's not, so you're explicitly defining the initial stress state. You're not using the soil weight to determine an initial stress state. We would typically use this in deep models such as tunnels where it's unrealistic to define the whole profile view of the model. Instead, we would only look at a small section and then apply a field stress that equals what we would expect for the stress state on the tunnel liner. Again, because we are explicitly defining the magnitude of the initial stress state in the principal directions, we don't necessarily have equilibrium involved. So if your summation of forces in each of the principal directions does not equal 0, it's feasible that depending on the boundary conditions that you would not have equilibrium guaranteed. And in that case, you'll get some kind of error or some result that would show that you're not reaching convergence. For the field stress option to work, you would need to set all your boundaries. You must be fully fixed. So the obvious question now, for most models, we'll be using either the K0 procedure or the gravity loading procedure. And then the question is, which do you use if you have a case where you have soils that have some level of overconsolidation, so OCR is some value greater than 1, and you have an initial shear stresses generated. Shear stresses can be generated from non-horizontal soil layers or from slopes in your in the surface. So we have a solution for this. We would define the initial stresses using 2 phases. So we would use the K0 procedure. And then after that initial phase where we've defined K0 as the calculation type, we would have a following phase, which would be defined as plastic loading. We wouldn't make any changes to the geometry, and we would let PLAXIS calculate the shear stresses from the plastic nil step. So the way this would work is we would have an initial phase with the K-0 procedure defined as the calculation. We would define a new phase as phase 1 as a plastic calculation, but no changes would be made in the model. Hence, this is why it's called a nil step or null step. PLAXIS will detect the lack of equilibrium or resulting from the K-0 procedure and then solve it. What this means is it will generate the shear stresses inherent in the model. And then in the following phase 2, we'll reset the displacements to 0, and then we'll begin to run our analysis. And this will generate the correct initial stress generation. I have a handy illustration that captures this concept in the following slide. So suppose we had a soil here. Let's say the soil has an OCR value of 3. So we'll have to use K-0 as the initial phase. This is the initial model geometry. What will happen, PLAXIS will do a K-0 calculation, determine the principal stresses and the magnitude of those principal stresses. You can see here they're illustrated as these red crosses inside the soil element. So this would be the initial stresses from the K-0 procedure. From the plastic nil step, it will incorporate the shear stress generated from the slope, and then we'll get a change in the orientation of the principal directions. And then once we reset displacements to 0, or from the stresses after the nil step, we'll mobilize displacements, and then we need to reset those displacements to 0 once we begin phase 2. Here's another diagram that illustrates the concept well. So suppose we're working on a project site. The project site has existing buildings around, so the soil has some level of stress history and some past loading. What we'll do to generate the initial stresses of the soil is we'll begin with a clean geology here, so a clean soil polygon. In phase 1, we'll incorporate this, the loading from the left building. So this will capture the stress history from adding this applied load. In the next phase, we'll incorporate the loading from the building to the right side of the project site. And this will capture the stress history from the addition of the second building. We'll reset displacements to 0, and then we'll begin to build our PLAXIS model of the project site. This is important just to illustrate that sometimes multiple phases will be needed to capture the stress history of the soil, because sometimes the stress history incorporates many different factors that may exist in the site prior to our construction. And to do that, we'll need several calculation phases to actually capture that. So some important notes here. To generate the correct initial stresses, we need to capture the correct initial project conditions. So we'll need to apply loads in the same chronological order as was done in reality to capture the correct stress state. If we're working with undrained soils, we need to define the soil as an undrained soil. And if we have past consolidation behavior, we'll need to run a consolidation analysis. This is especially important in cases where we have soils with the tendency to show creep behavior. So if we're using soft soil creep, for example, we will need to specify some time interval for the consolidation process to run. Because creep is a time-dependent behavior, we need to define a construction time, and this will determine the magnitude of the creep that will be present in the soil. And then once we begin our, after we've defined the phases that capture the initial stress state, we need to remember to reset displacements to 0, because we need to set a datum for our project to run. So reset displacements to 0 once we begin our analysis after the phases that define the initial stresses. Okay, so with that being said, that is my presentation. So I will, we have some example questions that users have submitted to us in the past. But if you have your own questions, please feel free to use the chat window, and we will answer as much questions as we can in the hour. Thank you, and please write your questions in the either the team chat window, or you can send it in the Q&A box. So we will begin to answer the example questions that users have sent to us in the past. I'll throw that over to Facile to answer the first one. So Facile, I got a question for you. What is the difference between POP and OCR, and when to use what?
Yes, thanks, Sean. Before I answer the question, I would just like to show a visual of the initial stress generation using the field stress. For that, we have a very nice video demonstration. I'll just show it by sharing my screen. Okay. Yep. So if you can see my screen right now, see, this is at our Bentley Communities website link. It shows that you can generate field stresses using the principal stress directions as mentioned by Sean. So you can create different soil clusters depending on the strata that you have and assign the stresses in the principal directions as shown. And then you can also view the stresses, whether they have been generated correctly or not, by going to the stresses menu and checking the principal effective stresses. Here you can see that the stresses are not varying like uniformly. They are like discontinuously varying as being specified in the input. So it's a very interesting feature. When you have a very complicated geometry, you can use that. All right, so first question. Let's see here. Difference between POP and OCR. Okay. So POP is the past overburden pressure and OCR is the overconsolidation ratio. Here again, I have a nice visual to show here. It's right here. So for example, this is the top level, which shows the soil level in the past, and now the present day level is here. So in that case, you will have an overconsolidated soil. And so the overconsolidation ratio is determined by sigma P, which is the past maximum pressure, over sigma Y, which is the current vertical pressure. Whereas the POP, which is the past overburden pressure, is determined by subtracting the past pressure minus the current vertical pressure. So this way, you can see there is a slight bend in the stresses, and so there's a shift in the vertical stresses because of the overconsolidation ratio. And so what are these? So if the soil is overconsolidated, there needs to be an adjustment in the coefficient of earth pressure K0, which can be done using the OCR or the POP. POP, which is the past overburden pressure, is more preferable than the OCR since it describes the deformability process more accurately. Also to note here is that if you specify a very low K0 value using the K0 procedure, it can lead to stresses which may violate the Moore Coulomb failure criteria. And so what PLAXIS will do, it will automatically reduce the lateral stresses such that the failure condition is satisfied. So the stress points will be in the plastic state, and you can see those in the output. This will result in stress field which is not in equilibrium. So it is generally preferred to generate initial stress field that does not contain the more Coulomb plastic points. Also, you can use the K-Knot procedure followed by a plastic nail step. This way you can account for the OCR of the soil and the slope layers. Once you generate the initial stresses using the K-Knot procedure, it will not have generated the shear stresses as mentioned earlier, and your model will not be in equilibrium. So you will have to introduce a plastic nil step. And also, once you generate the stresses, whether using the OCR or using the POP method, you have to verify your input stresses, whether with field measurements or something, with some hand calculation, so that you know that you have generated the correct initial stresses. Because if the initial stresses are not correct, then all the related later modeling and results will be of no value. Also, you should not use gravity loading when the soil is overconsolidated, because we don't have the option to use OCR or POP with gravity loading. We only have that when using K-Knot procedure. But there is a method of adding overconsolidation when you are using gravity loading. And the procedure that we recommend for overconsolidated soils, if you're using gravity loading, is that you basically follow 3 steps. You first load the soil to increase the stresses. You then remove the load, and then you check the stresses and OCR value in the output. Then if you're satisfied, you can continue with the analysis. Otherwise, you have to change the loading and then repeat such that you can get the correct initial stresses. So that is pretty much the basic idea behind the POP versus the OCR. Sean, you want to take the next question?
I will. Thank you, Vasil.
No problem.
So to summarize that, summarize an important idea that Vasil mentioned, whenever we have soils that are overly consolidated, we must use a K-Knot initial phase. We cannot use gravity loading ever if we have soils which have OCR values greater than 1. If you do that, you'll get an incorrect initial stress state, and that will make the analysis worthless moving forward. Okay, so another common question we get over at PLAXIS is a user has asked in the past, can I have spatial variability of the pre-consolidation pressure under an embankment? And we have a hint, so the answer is yes. I will show that to you where that option exists. So I'm going to share my screen right now. Let's see. And then I'm going to open a PLAXIS window here. Okay, so we got a PLAXIS window here. If I go from the borehole window, if I go from soil layers to the pre-consolidation tab, I can manually input the past overburden pressure or pre-consolidation pressure in these cells here. So we can define the stress history using boreholes rather than defining it in the materials window. So that's an option we have. And you would find that under the pre-consolidation tab in the borehole menu. Okay. So Fasil, do you want to, I'll pass off the next question to you.
Sure.
What is the influence of the over-consolidation ratio on the structural forces? So suppose you have a plate, or you have some embedded beam, or some structural element inside your PLAXIS model. How would the OCR affect the structural forces that PLAXIS reports?
Yes, so the OCR, which is over consolidation, it mainly affects the stress strain behavior of the soil. So therefore, any soil structure interaction will be affected accordingly. So for example, with an increase in, for example, if you have a retaining wall and you have an over consolidated soil, the at rest and passive earth pressures will increase on the retaining wall compared to a normally consolidated soil. Also, if you have a over consolidated soil, you will have lesser vertical settlements. And so if you have a concrete slab, which is modeled as a plate or a soil volume, it will deform less vertically. And also, especially when you are doing time sensitive analyses, such as a um, dynamic analysis or a consolidation or something, just time sensitive analysis, you will have a delayed deformation response because the soil is overly consolidated. It will have a little stiffer behavior. So your structure will also output a delayed deformation behavior. Also, when another example is that, for example, when you are driving piles in an over consolidated soil, and we have a tutorial example for pile driving, usually it's a very short term analysis, undrained analysis, so it will generate negative pore pressures due to the dilative tendency of the soil during shearing. So it's a very time sensitive short term analysis. And so these negative pore reported pressures affects the effective stresses in the soil around the pile, and it will actually increase the effective stresses of the soil, making it more stiffer, and it will affect the pile movement. And this is what actually causes the difficulty in driving the piles in over consolidated soil. So depending on the type of structure you are modeling and the short-term or long-term behavior you are modeling, you will have a different behavior, and it depends on case to case what it's going to be. So I just gave a couple examples, but there are a whole bunch of other situations that can happen.
Thanks, Fasil.
Yeah.
So we have a next question.
Yeah, I can take that too.
Okay, sure.
So yeah, for which models are the OCR values important, and what are the effects? So usually, advanced soil models, not taking into consideration the molecular model, they take into effect the over consolidation. So it requires the information about the OCR or the POP. So for the molecular model, the default K0 is determined using the Jackie's formula 1 minus sine phi. And so for advanced models, which is the hardening soil model, HS small strains of soil with creep, modified cam clay, and others user-defined models, the K0 NC parameter, which is the K0 normally consolidated, is influenced by the OCR and POP value. So, for example, if you look at the UBC, University of British Columbia model for liquefaction, it is advise to the user that not to use the gravity loading for initial stress, and so the user is advised to use, like, maybe, so for example, uh, more cooler model, not the more cooler model, but the hardening soil or another advanced model to generate the initial stresses. Um, Same thing with the soft soil creep model. So in this model, the rate at which the creep strains occur, it depends on the OCR as well. So it should be considered that natural clays, they involve structure, while the soft soil creep model does not include these effects. So considering normally consolidated soft soil deposit, it would seem logical, to set the initial OCR value equal to 1. However, it will lead to unrealistic large creep strains. So in this special case, when you're using the soft soil model, it is our recommendation to use a K OCR value larger than 1, like 1.2, 1.4. And usually we have seen that these values give a good uh, initial stress for overconsolidated soils. Similarly, when we have like another model like the NGI-ADP model, it is recommended for this model to use the K0 or the gravity loading for the initial stresses using the Moore Coulomb or HS model, and not use the NGI model for initial stresses. So once you use the Moore Coulomb or HS model to generate the initial stress, then you use a plastic nil step to get everything in equilibrium. And then what happens is that the hardening parameter for the NGI model will be adjusted so that equilibrium is obtained. And then you can have a third phase in which you can switch it to the NGI-ADB model, and then you can add loading and stuff like that. So different models are dealt with differently when you're dealing with over-consolidated soils. And so you have to be very careful. You have to read through the manuals to understand how the model has been implemented, what is affecting the OCR value, and how to get the correct initial stresses. So these I just gave a couple of examples of different models. And so if you have your own UDSM model, you have to thoroughly check the implementation. And so, yeah, just be careful and read through the manuals about the theory behind, and also how to get the correct initial stresses. Sometimes we have already some hints provided in the manuals which tell you that this is how the procedure should be to generate the initial stresses. So for example, the models that I just mentioned, the soft soil NGA, I just read it through our material models manual. So these directions are already given. But if there is some confusion, you can always create a service request and ask for more details about that.
Thank you, Fasil. I would also like to add, we have a lot of good literature, not just about the material models, but also case histories and publications on our community's website. So if you go to Bentley Communities and you search in, for example, hardening soil or soft soil creep, it'll pull up a list of publications we've done and background literature on the on that search topic, as well as using the material models manual as a good resource to kind of understand how different soil inputs affect the soil behavior. I just would also like to add, for what Fasil has already said, that when we have simple soil models like linear elastic or Moore Coulomb, OCR will only have an effect on K0. So it will only have effect on the lateral coefficient of earth pressure, or yeah, K0, lateral coefficient of soil pressure. So that's for simple models. For advanced models, it could have influence on the yield function of the soil, If we're working with critical state soil mechanics, it's going to influence the plastic potential function. If we're looking at soils that have creep behavior built in, it's going to influence the creep rate. Creep rate, how fast the soil creep it's a long equation, but it's a function of the OCR. You can imagine that soft, normally consolidated soils will creep at a faster rate than a stiff, very overly consolidated soil, and that's incorporated into the model itself. So different soil models have different effects depending on the OCR. For simple models, it just influences the K0 value, or the coefficient of lateral earth pressure. Okay. With that being said, I want to say thank you, and we will begin answering questions that you have submitted in the Q&A box. So I will grab the first one. So we have a user that asked, is a plastic nil step procedure provided in any of the online training examples? I do not believe so. I think this is a case where we will need to build the model ourselves. Our tutorials, for the most part, have cases where the soil is either normally consolidated and has an initial K0 or gravity loading phase, or is overly consolidated and has a K0 initial phase. So the plastic nil step is kind of an advanced procedure that I do not believe is in the tutorial manual. Facile, I got a question for you. For undrained material, for undrained B material, PLAXIS is it true that PLAXIS will set K0 equal to 1 by default as phi equals 0? Or should we manually set the K0 equal to the Jacobi equation, K0 equals 1 minus sine of phi for undrained material? Can you quickly talk about the initial stress generation using undrained B?
Initial stress generation. I would say, I'm not much familiar with this. Can you add your comments on this question?
Sure. Okay. Yeah. So for undrained B, it's important to note that undrained B simply means that you define an initial shear, or you define a shear strength of the soil, right? So you would define an SU. The stiffness and the K0 behavior should be normal behavior, right? So for undrained B, we would need to define in the initial tab, we would need to define a K0. So let's just say, for example, here, if we use more Coulomb, we set this to undrained B, we would need to go to the initial tab, set it to manual, and then manually put in our K0 value. I can share my screen here to show that. Share. Okay, so here I've defined a hypothetical soil model using more Coulomb and undrained B. From there, I will set the K0 determination equal to manual, and then I will need to manually input my K0. So this would be the case for undrained B. Indeed, it is true that using undrained B, the friction angle would be equal to 0 because the shear strength of the soil is constant over all stress paths. Okay. So we have a, do we have any other questions from users out there?
I don't see any questions more.
Well, that's good news. I hope this presentation was clear. Facile, do you have any concluding remarks for today's answer hour?
I would just say that if you are listening at the recording and you couldn't listen this right now, you can, and if you have more questions, you can always create a service request and send it over, and one of our support engineers will be happy to get in touch with you to answer your questions in detail.
I would also like to add that the topic of initial stress generation and the influence of parameters like OCR and POP on your model can be quite complicated depending on what soil model you're using. So if you ever have any doubts, please go to the Material Models Manual or the Bentley Communities and research the soil model you're working with. And it's important to have a good grasp of how the soil model works before you start building your model. With that being said, I'd like to thank everybody for attending live today. If you have any questions, don't hesitate to email us using a support ticket or reaching out to us directly. And with that, I will throw it over to Gina, and she will give her concluding remarks, and we'll say goodbye. Thank you.
Thank you, Sean and Fasil, and thank you for those of you who joined us and those of you who have listened to us in the recording. A survey will pop up after this concludes, and we do appreciate your feedback. Otherwise, we wish you well, enjoy the rest of your day, and we hope to see you on future answer hours or coffee corner sessions. Thanks, everyone. Goodbye.